Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very pleased to welcome Andrew Brownsword to Microsoft Research. Andrew works at Electronic Arts, has worked there about 17 years, and currently spends a lot of time dealing with parallel hardware. So today Andrew is going to give his perspective on parallelism and game development. Andrew gave a shorter version of this talk at CGO back in March, and I asked him to come here. So I'm looking forward to seeing the longer version. I thought the CGO talk was really fascinating, and I think he'll provide some good perspective and some realism on our discussions about parallelism here. Thank you.
Well, thanks for coming. Thanks, Dave. I was at CGO at the invitation of a fellow at Intel because we had gotten to chatting about some of the stuff they're doing there and some of the problems they're having with software developers taking advantage of their new hardware and problems they're anticipating going forward. And so he invited me to come down and be the application developers speaker at the data parallel workshop because I have a bit of a bent on data parallelism, as you will see shortly. So this talk is motivated largely by hardware and the desire to get as much performance out of the hardware as we can. Games are constantly pushing the envelope, and we find that you really can't take enough advantage of the machine. We're just pushing them harder and harder, and this latest generation of hardware has departed from the traditional programming model fairly radically, because now not only do we have multiple processors, but the pipelines have gotten very deep, SIMDs become very important, etc. And the programming model now has become very bandwidth and latency limited. Achieving high throughput on these machines is challenging, and you really have to optimize your software for maximum throughput, and you need maximum throughput in order to achieve maximum performance on these machines. No longer is computing cycles the limiting factor. Now it's how much data and how long it takes to get it into the processor and back out again. So there's a variety of levels of parallelism in these machines. There's multiple cores, of course, and this always gets the most attention. Oops, that's a button. The multiple cores get the most attention because it's the most obvious thing. So the Xbox 360, for example, has a GPU and a 3-core PowerPC processor, and the PlayStation 3 has the Cell processor, which is a PowerPC core, and it has 6 or 7 additional, they're called SPUs, and they're sort of special purpose, more limited but higher speed processing cores. And it has a GPU as well, of course. And PCs these days are starting to have dual core, quad core, and we anticipate even more cores in the future. So dealing with multiple cores is obviously a big step. But there's also instruction level parallelism, and this gets not enough attention because people compile their code and they see how fast it runs and they sort of take for granted, well, that's the speed of the machine. But when you actually go down and you measure how many instructions per clock cycle and how much work is being done per clock cycle, you start to discover we're only really about 10% using 10% of the hardware's capabilities. And, you know, 10% is not enough. We really want to be able to push it a lot farther, because if we can do 10 times as much as our competitors are using the machine for, we can make a better product, sell more games into the market, etc. And then a third, less obvious form of parallelism is the memory interfaces are all out of order, and taking advantage of that is really critical because these machines are bandwidth and latency limited. So taking all three things together, it's necessary to take full advantage of them in order to get maximum performance. And the problem is, to take advantage of those things, you're diverging from the traditional programming model that we were all taught in school. So programming model we're using is embodied by C++. Problem with C++ is there's actually no concurrency built into the language. None. there's no concessions or observation that there's concurrency within a single thread of execution, and there's no support in the language, per se, for multiple cores. Now, you can have libraries and stuff, and you can have special extensions to your compilers that give you access to these different kinds of things, but that's different than it being built into the language. So to a first approximation, C++ is really not a whole lot different than ALGOL 68 or any of those languages. You added objects and whatnot, but from a performance perspective, it really hasn't changed a whole lot. Excuse me. And that means to go fast, you really have to write non-standard C++ code. And at EA, we're cross-platform, we're fairly platform agnostic, therefore some of our products ship on 5, 6, 7 platforms, and they're all different. So if we write one piece of code, if you keep it generic, keep it standard, it'll run on all platforms, but you really are going to miss out on the performance, the peak performance potential of the given platform. And and there's been attempts at having the compilers do a better job to deliver better performance without the programmer really having to know anything. But so far, we've been very unimpressed by the auto vectorization capabilities and the OpenMP extensions. I mean, OpenMP is an extension to the language, so it's non-standard. Plus, it doesn't really have the right model for the kind of stuff we're trying to run on these machines. And auto vectorization, I have yet to see an example where it actually made the code go faster. It just doesn't seem to work at all. And quite often, the compiler just throws up its hands and gives up. So why is that? Well, this is sort of my opinion. The compilers are really constrained by the expectations we place on them. I mean, there's the programming model that's sort of inherent in the language itself, and there's the huge amount of code it's expected to compile. I mean, just our code bases are millions of lines of code, and we have a whole bunch of them. And if the compiler really strays too far from the beaten path, you're going to break our code base. And then there's the programmer knowledge that surrounds this as well. The programmer writes something in C++, back of his head he's got an idea of what that means and what that's going to turn into in terms of the machine code. And if you start breaking those kind of expectations, the programmer is going to be somewhat astonished, and astonished programmers are something to be avoided. And the compiler guys that I talk to occasionally, they always say, oh, we could do that in the compiler. So I turn around and I say, well, why don't you? Oh, well, we're too busy supporting the C++ standard, or if we did that, there would be corner cases where we would... I mean, it boils down to that the language is extremely complicated, and adding to it adds additional complications on top of a big pile, and it really just makes a messy situation messier. And the language itself, from this point here, too much emphasis on how to do something. I was trying to figure out how to phrase that, and really when we're writing C++ code, you're telling the compiler exactly what the machine should be doing, and the compiler doesn't have any freedom to do things a bit differently. We would really like to be able to say, well, this is what we're trying to accomplish, and let the compiler figure out the best way to accomplish that on the available hardware. Currently, the compiler is far too close to the hardware. So, I've seen many cases now where we write simple, portable, but entirely reasonable C++ code. And it's the right algorithm. And then we go and we optimize it. And, I can spend days, weeks. I've even spent a month on one function, making it go faster. And I've seen cases where it goes 2 orders of magnitude faster compared to the simple scalar code. Now, 10, 15 years ago, when I was writing code on the original Pentium or thereabouts, the compilers would typically get within 20, 30% of what I could do by hand. So I wouldn't bother doing anything by hand because the compiler was close enough. I had better to go and improve the C++ code elsewhere and get a win that way. But now I'm spending a great deal of my life, entirely too much of it, hand coding and tweaking and optimizing individual low-level functions. And I'm getting enormous wins without even going multi-threaded. You know, getting a computation off of the main core is a big win, and then I go in and make it 8 times faster. I mean, this is not the kind of thing that we're just going to say, we don't need to worry about that. And another thing to note is most of these cases that I'm talking about here were already cache friendly. Stuff was already arranged so that data locality was pretty good, and I'm still seeing 2 to 8 times, sometimes higher, 10 or 20 times. And in fact, when it's not cache unfriendly, we've seen speed-ups of, I have one case that was 350 times faster. I didn't change the algorithm, I reorganized the data, and I optimized the code using intrinsics. That's a big difference between the scalar code and the optimized code.
Do you optimize in assembly or?
No, I optimize in C++. It's completely non-portable C++, of course.
What is the reason for this?
I'll get into that in a bit. So, one reason is C++ in games, and probably in any software, definitely in any software, designs, object-oriented designs are quite often, and I call them naive. That's a bit unfair, because what it really means is they are designed from the programmer's perspective. What's the object model that you would like to have? People don't spend enough time thinking about what's the object model that the hardware would like to have. And C++ is so close to the hardware, it can't take your conceptual model and translate it into the model that the hardware would like, because it doesn't have enough flexibility. It doesn't have enough knowledge about what your intention was. Therefore, you end up with these designs where even when they call in the expert optimizer late in the game, the design is so broken from a performance perspective that late in the project development cycle, we can't restructure the game sufficiently to fix the performance problems and then actually get around to fix the design problems and then do the optimization work. Quite often when I sit down and I'm going to go to optimize a piece of code, I take a first look at it and I go back to the author and I say, well, re-architect it like this. Bang, bang, bang. Give him a list of points of things to change. He goes off and he does that. When he comes back, the design is now amenable to optimization, and presto, I can make it go 10 times faster. So, I mean, within EA, I've been giving talks for a couple of years now about how to design your software so that when you call me over to optimize it later, I can actually do something. I mean, I'm really quite selfish. I mean, I saw the writing on the wall, and I know a lot about this stuff. I knew they were going to come and say, Andrew, optimize this for us. But the problem was I ended up with these designs that were broken. So what I started trying to do is do these talks and motivate people and say, look, design it this way so that when I do, or some other optimizer does come along and want to optimize your low-level code, we can make it a whole lot faster. It turns out it's really hard to do that. People, when they're not properly motivated, when they really don't deeply understand why their code is slow or how it could go fast, they don't internalize it, and then it doesn't reflect in the designs. So I understand the low levels well. I can come up with designs that are going to perform very well. Most of the programmers can't. Therefore, while I've made some advances, and we're sort of getting a bit of ground, typically people are using all the facilities of the language like they want to use it so they can design nice conceptual models, but it breaks optimization later. So what is naive object-oriented design? Yeah?
And having looked at some of the designs that were inefficient that you looked at, were they actually nice conceptual models, or
yes.
Was it? Okay.
Yeah. Typically, and this is sort of why, typically a naive design ends up with a relatively low computational density. There's a lot of infrastructure and organization in the code on top of the computation, and programmers tend to not want to fix the whole problem all in one place. Instead, okay, well, let's solve this bit of it and then this bit of it, and those all go into separate functions and they get buried under call stacks, and you end up with this massively divided problem. And the way that you get speed when you have concurrent hardware is by having lots to do all at once, because now you have a lot of things you can do concurrently. If you don't have lots to do at once, there's very little to be worked on. There's nothing to do concurrent with it, right? If you have a million operations to do in one place, now you can figure out how to do them all at the same time. If you have one operation to do at a given place, there's only one thing to do. How do you figure out what to do concurrently with it? Object-oriented designs also typically have poor coherency in terms of both instructions and data. The data tends to be lying around on the heap. The code tends to be oriented towards this one, do this one operation on this one object, and now do this operation on this object. It's sort of all wrong from a coherency perspective. Deep call stacks are evil because, if I want to optimize the low-level function without disturbing the whole design, I'm stuck with very little data and very little operations down at the bottom of the call stack. And then the other thing is you're chasing pointers through memory. This is just absolutely death for the modern memory subsystems. And inefficient use of hardware. So all this modern hardware gives us nice capabilities. In particular, the SIMD registers have awesome potential for throughput. To give you an idea, on the Xbox 360, there's 128 vector registers. Each one of them holds 4 floating point numbers, and it has a throughput of floating point multiply add operation per clock cycle. And almost in most of our code, we never take full advantage of that, not even close. In fact, it's so bad that we could switch from using the vector unit to using the floating point unit, and we would not lose any performance. In fact, we might gain performance, because what happens in these long pipeline machines is it stalls between dependent operations for 10 or 12 clock cycles. And then a classic thing is, since we deal entirely in 3D, programmers have these 3D vector 3s and vector 4s, which represent a position or a vector in 3 space. And they think in terms of these things. But when they see a register that holds 4 floating point numbers, they go, oh, hey, look, my vector 4 fits in there perfectly. But SIMD stands for same instruction, multiple data, right? Same semantic operation, same actual operation for each data element. But X, Y, Z are semantically different, right? They're 3 different axes. If you do a cross product between them, you want to do something different for every X, Y, and Z. There's some operations like dot products that happen to be the same, but if you do anything more than a trivial operation, it's going to want to do different things to X, Y, and Z, and it's no longer a SIMD operation. So you end up wasting a lot of time shuffling data around inside of your registers. And then across multiple cores, you of course end up with this problem of too much thread synchronization. If the design wasn't carefully thought out in advance, how things are going to be split so that they don't have to synchronize, they're going to end up synchronizing too much. There's an incredible tendency, if somebody builds a subsystem and then says, how's this going to work on a new multi-threaded machine? The tendency is to, oh, I'll just make it thread safe. Okay, well, what does that mean? And what are the ramifications of that? And they don't think about it. All they do is they go sprinkle mutexes in, or they don't sprinkle mutexes in, and you end up with either too much synchronization or not enough, and you end up with really horrible bugs. So what does efficient object-oriented design look like? Well, first of all, data layout is absolutely critically important. Like I said, bandwidth and latency are the performance bottlenecks on these machines, and the way you optimize for that is how you structure your data. Sometimes you find that a single conceptual object, a car, for example, doesn't get stored as a structure in memory in one place because there's a whole bunch of different things you do to a car. And the different algorithms you apply to the car might need this quarter of the structure, and the other algorithm uses that quarter of the structure. And so to get maximum performance and maximize bandwidth, you sort of want to organize it along the lines of what algorithms are going to be applied to the data, which is completely cross-grained from the way C++ wants you to build objects. Algorithms in efficient code will operate on vectors of uniform type. I mean, basically this means you're going to take the same code and you're going to apply it across a large array of data and do the same thing to it en masse. And if you have a really long array of data, you can start using SIMD, you can start splitting it across cores, all sorts of other things you can do to make it go a lot faster. Polymorphism is the complete antithesis of that, right? If every object you want to do something different, now you lose all your code locality, you have these costs of doing virtual function calls, your data is non-uniform in size, becomes harder to prefetch. So what happens in efficient designs is we try to push the polymorphism up a level. You say, here's an array of this subtype, here's an array of that subtype, and then you apply a uniform algorithm to the uniform array of data. You also try to make the algorithms as computationally dense as possible. Currently, hardware is capable of around about 15 floating point operations per float that you read and write from memory. Most algorithms don't get anywhere near that. Consequently, most of them are memory bound. It doesn't matter how much you optimize them. The processor is sitting around idle while it's waiting for data to come in and out. So big optimization is combining combining different pieces of computation into one pass across the data and looking at it as sort of a data flow model. Data is going to move from here to here and be transformed by this algorithm in the process. And that lets you build up the density, and you can have huge amounts of instructions in the inner loop as you process this data, and you touch it a minimum number of times. And you also get rid of branches, because of course branches on at least the in-order machines are just completely heinous. And if you're branching per data element, suddenly you've blown out your ability to use SIMD, and you're doing 4 times less math typically. As a result of all that, efficient APIs tend to be system oriented. Rather than talking about, I want to do this to this object, you say, I want to do this to all of these objects. Right? If a system contains 1,000 objects that represent the characters in the game, you don't want to say to each one, you don't want to have a loop outside the system saying, okay, do that to him, do that to him, do that to him, etc. Instead, you tell the system, do this to everybody. And the system is optimized to do that operation. And this last point down here is it's just not natural, right? People who learn C++ have a certain way of thinking about objects. They want to program the conceptual model. They don't want to program in the efficient ways. Getting people to change their ways is really hard, and it tends to impact their productivity. And most programmers just don't understand the hardware well enough in order to be able to see the motivation for it. So I use the term vectorization. I don't know what the real definition of it is, but this is how I've adopted it. I needed a word to describe this when I talked about it inside of EA. What it boils down to is everything you do to make a single thread go faster, optimizing it for throughput, boils down to vectorization. And that covers a lot of stuff, and I intentionally make it cover a lot of stuff because most people look at the SIMD units and misunderstand immediately for how they're intended to be used. The hardware is intended to be used on long vectors, not on 4-element vectors, right? The objective here should be use the 4-element wide SIMD unit, but fill the pipeline. And if the pipeline's 10 stages long, now you have 40 elements that you have to worry about, not 4. If you're superscalar, now you have multiple things going on at the same time per clock cycle. You have to worry about how your memory subsystem's working, so you're prefetching data or you're DMAing it in or whatever. All of these things combine, and I just blanket them with the term vectorization. Once you vectorize stuff, we've discovered that it maps extremely well into the multi-core realm, especially where the multiple cores are vector processors. So the PS3, the 6 SPUs, they're vector processors. There's no two ways about it. You can write scalar code for them, but the scalar code is less efficient than the vector code. Even the PowerPC processors that are in the Xbox 360 really at their heart are vector processors. There's a whole bunch of stuff in there to make it look like they're good general purpose processors, but they go a whole lot slower unless you feed them vectorized code. In order to do vectorization, you really want to choose algorithms that are vectorizable. In games we have a lot of flexibility, so we can say, well, we won't do it that way, we'll do it this way. It's sort of less correct, but who cares about correctness? We just care about fun, right? So because we have a lot of choice, we tend to have a bit more flexibility in how we go about things. Doesn't mean it's always true, it just means we have a bit more latitude. And importantly, though, designs have to be vectorizable, and this is where typically we get really nailed. Swapping a low-level algorithm is easier than sort of uprooting the whole design and changing how it exists in the system and how people use a system that exists within the overall game architecture. And vectorization boils down to typically data parallel, although a more flexible definition of data parallel than I think is typically used. This slide is because I use this term, I thought I should define it, and I guess it's kind of an interesting point. The main computational multiprocessing model that we've adopted inside of EA is this thing called the job manager. And it boils down to asynchronous function calls. A job is an asynchronous function call that you want to make. We have a mechanism for arranging these asynchronous function calls into a dependency graph, so job A can't proceed until job B is done, that sort of thing. And these things all get dumped into a queue, and then the other processors pull them out of the queue and do their work as fast as they can. This really, it's not unique to EA by any stretch. We've seen talks at various other, game conferences that talk about this sort of thing. I think ours is perhaps a bit more refined, and we've had people working on it for a while now. So we have this architecture, it's cross-platform, and we try to push our expensive computations out into these asynchronous function calls that we call jobs. Jobification is just what I call the process of taking computation, pushing it out into an asynchronous job. I'll come back to that in a bit. So I mentioned data parallel. Modern hardware is very, very good at it. There's no two ways about it. That's how I get this big speed-ups when I do optimizations. And it's because we have deep pipelines, SIMD, large register sets, lots of state in the machine. Throughput and data parallel sort of go hand in hand because it's easy, relatively easy. Nested data parallelism is a term that I first came across because of the Intel guys at the CGO conference. I don't really know the official definition. I just know it broadens the typical definition of data parallel. When you say data parallel to most people, they have a really narrow perception of what that means. Nested data parallel expands that. I think my definition is probably even broader because I'm more familiar with what the hardware is actually capable of. And I don't know enough about nested data parallel to say this with any certainty, but the hardware is probably more capable than the sort of general model that nested data parallel, certainly than sort of traditional data parallel describes. And then, when I talk about data parallel and wanting data parallel tools, quite often I get this reaction that says, yeah, but that doesn't solve all the problems. I have all these problems that just won't, no matter what, fit into the data parallel model. Well, first of all, you probably haven't tried real hard because there's a lot of problems. If you really worked at it, you could figure out how to recast them so that they are data parallel. And second, I don't really care if it doesn't solve everything. We have a whole bunch of problems that can easily be cast as data parallel, but it is really miserable to code them and get maximum efficiency in C++ right now. So if we had a tool for this and we could safely rely on it working and getting decent performance, and by decent I mean even within a factor of 2 of what's possible, then I'd move on to the other problems that it didn't solve. So maybe that's a straw man, maybe it isn't, but I do hear that a lot. I guess I just said most of this. We have lots of stuff that is obviously data parallel. There's a fair bit of stuff that isn't data parallel in games yet because it's too hard to code it. If it was easy to experiment with these things, we could turn around and give it a shot. Does this work better than that does? It does. Great. Let's go that way. But right now, it's just too much effort to code it multiple ways and actually get representative performance. That's really the important part, and I'll come back to that in a minute. Yeah, games have some advantages. I already mentioned that. So we do have lots and lots of pieces of code. We had the guys from Mercury Computer come in because we knew they were writing optimized code for some of the IBM processors, and we said, so do you have any magic tools? And they said, well, no, we just get the client to send us the algorithm they care about, and we optimize it. The algorithm you care about? Yeah, well, everybody, they care about that kernel or that FFT, or most of their clients have a thing they want to run on their high-speed processor. That's why they're buying the high-speed processor. In games, we get handed the hardware and told, put all of this stuff on it. Here's the feature list. Make it go real fast. And we end up with, I could work the rest of my life on functions in one existing game and never have it fully optimized. So here's an example of what I'm talking about. I tried to figure out how to have a data parallel coding example where I could convey the difficulty, right? I mean, this over here on the left is the scalar version, and I basically took a printout of the code, scaled it all the way down, and colorized it a bit, shoved it there. And then I took a printout of the code after I was done with it after 2 months of coding. And it runs 4.5 times faster, or 4.25 times faster on the Xenon. And there's 4.25 times as much code simply with looking at the number of pages. But if you look at on each page as well, the lines are all sort of bushier. So there's a whole lot more code. And anytime anybody on that game team goes into that file, they go, ooh, and they don't want to touch anything. The one time somebody did, he halved the performance of the algorithm by inserting one line of code because it was a branch. It just completely threw off the pipelines. And so I had to go back in and fix it. This is not right. We're supposed to be programming in a high-level language. Yeah, there's a question.
So is that because you had to vectorize it within the C++ framework that existed, or would that be the expansion in code if you sort of had, were able to, like, say, retool at a higher level and then vectorize just this one routine?
This particular function, I guess conceptually I have a model of how I would have liked to describe it at a high level. I think we're a whole long way away from being able to have a compiler that could actually generate that from the concise description. But in general, if I had a higher level way to describe it and could rely on the compiler to get to optimized code, it could generate this mess all by itself, right? Does that answer your question? I'm not sure
I don't know. I mean, certainly, well, at least my experience is going from sequential code to vector code on things like vector machines certainly doesn't cause that explosion of numbers of lines. So I was sort of surprised.
This is the most extreme example I chose.
Sequential MPI causes that, I agree.
Typically it does expand the code. I usually see a doubling of size for a factor of 4 or 8 of performance. But it depends on the algorithm. This one was particularly heinous. And regardless, this code, the vectorized code, is always less understandable by the programmers because they're looking at intrinsics they don't understand instead of looking at straightforward math that we're all taught in grade school, right? I mean, instead of infix notation, they're looking at vector intrinsics and select functions and stuff like that. So, again, there's no concurrency in the language, which is part of the reason for it sucking. And, I mean, really, there's no way to tell the compiler you're doing a data parallel thing aside from the intrinsics. And even then, the compilers these days typically don't really understand the intrinsics aside from just allocating registers and dropping the instructions in the instruction stream.
Usually these code fragments that you try to vectorize or optimize, how big are they?
Not enormous, like a couple screenfuls of code, so you're talking a couple hundred lines. Not enormous. The rule of thumb is you want the inner loop sort of to have the state entirely in the register set. And these machines have 128 vector registers, so they can hold a fair amount of state sort of internally. And you load data, do a whole bunch of computations, blast it back out to memory. That's the typical paradigm. And the last one, again, is when you write something in C++, typically it has a very direct meaning, and programmers expect it to have a very direct meaning in what comes out the other end.
So is it fair to say that you're looking for something like APL as a...
I'll come back to that. So I've been blathering on about how I think C++ is shortchanging us. What comes out of poor notation? Well, here's this list, and it's all exploded on the following slides. So one at a time. C++ compiler limitations. You know, in practice, and we've been using C++ for quite a while now, so in practice, I mean, practically speaking, the compilers aren't aggressive enough, and we don't think they can be aggressive enough because every time the compiler or vendors try, they tend to start breaking stuff. So they move forward slowly, but they're also having problems keeping up with the very big language spec and dealing with this large legacy that they have to work under. And really, I see incremental improvements to compilers, but there's nothing really big promising coming along. Next one is, and this one's really important actually, a lot of the time in the games business, we don't have a lot of time. We're trying to crank out a product every year or two. We have tons of features to do. So for any given thing, we have to explore what does the runtime code look like? What does the pipeline look like to get data to the runtime code? How does it integrate with the rest of the game? How is the data authored? For any given feature, there's quite a bunch of stuff that's involved. And we can't afford to spend a lot of time exploring different solutions in the runtime to get optimal performance. Because, and this is really compounded because of the fact that it's very hard, even for me, to predict up front, here's an algorithm, how fast is that going to end up running? And really the only way to find out for sure is to go and do the week or month worth of optimization to get it up to maximum speed. And in this constrained time frame, while you're trying out 5 or 6 different solutions, you can't afford to spend whatever it is, a couple of months, just on the runtime component, because there's all these other pieces too. And typically if you're changing data layouts, that means you have to change your pipeline. Sometimes that means you have to go back and change your authoring solution. So just trying to rapidly iterate on different potential solutions to solve the feature problem, you don't have time to optimize it, so you don't really have a good way to predict how fast it could run and what performance impact it will have on the game. Because all this stuff has to run in pseudo real time, right? So, and then there's also this idea that the notation guides the path to the solution. And with this, again, it's like the C++ leads you down the path to the nice conceptual solution that you'd like to have. If you speak in English, you tend to think in English, and that guides your thought. And the same applies to C++. So it really constrains how you look for problems when you're using a given implementation language. I've spoken on this, the impact on software design. Since performance is governed by low-level details, your high-level decisions need to be guided by low-level details. If you don't understand the low-level details, it's hard to be guided by them. And our domain experts that are building the systems typically aren't hardware experts. Therefore, we have this problem of the people that are doing the design work aren't always experts in what can make it go fast. Time required to optimize. Optimization comes late in the product development cycle. I mean, it has to, because there's just too many changes going on earlier, and when you optimize something, you're taking flexibility away because you're sort of obfuscating it in order to make it go fast, and you're nailing it down. If you have to make feature changes to a piece of code after it's optimized, it's a heinous chore, and probably has to be the optimization expert that does that. The feature-oriented programmer can't make those changes. And we always have rapidly changing feature requirements. I think it's probably common across the entire software industry. I just know we have lots of pain that comes from that. And since it can take weeks or days for both vectorizing it and pushing it off onto other cores by Jobifying it, there's all sorts of issues that come out from maintenance and tuning, and not just the initial implementation. And each platform has to be identified. And if we have 5 or 7 platforms, that's really painful. In games, I mean, we have games that repeat and cycle every year. And typically that's the goal, is to get a franchise, get the code base working, get the product out the door, and then start on next year's version. That recurring business model means you don't have time to completely recode the game every year. Therefore, you have to maintain the code. Maintaining code that's in this form, I mean, at the bottom I say we call it write once, read never code, because it just gets so horrible that nobody, even the original author, wants to go back in. I mean, that function I showed you earlier, I dread the day, and I've had to go back in 3 times now to add features after the fact, and every time it's just mind-bending as I have to relearn how it works. And the complex code is this point about it's fragile and it's very easy to break performance. When I coded that particular function that I had up there on the slide back in December, there was a place where I made a choice about how one particular branch was going to work, and I was building a talk to teach people about vectorization internally about a month ago. So I went back and I know they're going to ask me how much speed up this particular technique gave. So I went back and I timed it again, and I had the timing numbers from the original optimization, and it was slower now. I'm like, what? And it turns out that the XDK had been revved a couple of times, and the guys at Microsoft had done a really bang-up job, and sure enough, the optimizer now sped up the original version of the code by a factor of 2, making my, this little piece of it, making my branch optimization a de-optimization. So I rejigged it a little bit, and it came out even faster than before. But it's just indicative of it. Stuff is fragile. The platform you're coding for is the overall environment, it's the compiler, it's the hardware. It's a very complicated equation. It wouldn't be so bad if it was easy to code this stuff and you could go back in and tweak it, but because it's so big and so detailed and just plain gross, it's painful. And again, we have lots of platforms, we have a whole bunch of different kinds of processors. Potentially we want to be able to run code on the GPUs, we want to be able to run code on, there's even physics processing units out there now, all different kinds of stuff. And if we have to hand code for each and every one, it's just not feasible. Yeah, and our pipelines are getting bigger and slower, and so because we're pushing more data through them, and so it's starting to get to the point where we have to start worrying about optimizing on the PC in the development process to make sure our build times aren't really slow. But nobody's going to spend this level of effort optimizing the pipeline, so, and it's all data parallel stuff, right? Processing. Sorry. Yeah. Game terminology. So you have authoring package where you create your data, and then there's a pipeline that takes the data in the authored form and converts it into whatever the game runtime will load. It's usually some binary format the game just loads into memory and uses directly. So there's a conversion and, what's it called? There's a conversion and massaging process. There's often lots of analysis that goes on at that stage of radiosity, lighting, and various other things happen. And a lot of them are imminently data parallel, but we don't have an easy way to code that to make it go faster. It's even hard to spread it across multiple machines. We have whole build farms and stuff, but we can't take individual algorithms and have them take advantage of all the hardware we really have. And then sort of a corollary to the first one is the hardware designers are out there trying to make hardware go faster and faster, and a few years ago they sort of ran into a wall where they couldn't just push the clock rate up anymore. But this really started before that, I guess, because to push the clock rate up, they make the pipelines deeper, branches get more expensive, and the programming model has been changing for a long time. It's just been not as obvious until suddenly they branched out and started going multi-core, or they started to go really heavy-duty SIMD, etc. And things are going farther in that direction, not less far. So we're going to see more and more cores. We're going to see more and more aggressive SIMD and all sorts of other techniques, I'm sure. And I mean, already the code's not portable. We can sort of hide. We can sort of hide some of the differences. So I actually code for the 2 PowerPC cores and the Cell's SPU core, and I can take the same code and cross-compile it because I have a bunch of macros and stuff. So as long as I don't use fringe features too much and stay within what my macros define, I can write one piece of code and compile it on 3 platforms. It's actually not optimal on 2 of the 3, but for one of them it is. So I choose the slowest one, optimize for that, and the other ones are fast enough. But doing that, I can't do that for the PC because it has so many fewer registers. It's an out-of-order processor. I mean, I'm dealing with stuff at the level where those features make a big difference. And if I tried to cross-compile my code that assumes 128 vector registers, and I tried to compile that on the x86, it falls over compared to what it could have been if I had coded specifically for the PC. And the farther out the hardware guys go and the more diverse their hardware gets, the worse the situation's going to be. So, having told you all the bad things about the notation, all the reasons why it impacts us, what would a new notation look like? How am I doing for time? Oh, jeez, I better hurry up. Just a reminder that this is from a game developer's perspective. I have really tunnel vision. It's got to be familiar to C++ programmers. You know, be part of the family of C languages, just because it's familiar and accessible. And we have a lot of programmers, and if we want them to use something, it has to be familiar and accessible, easy for them to pick up. That is actually really, really important. You you know, the shader languages for the GPUs, HLSL and the others, they were adopted very quickly and very greedily by the rendering guys. And part of the reason was it looks just like C, right? It's really close. It's part of the family. You don't have to learn obscure notations like in something like, well, Haskell comes to mind, but it's just familiar, and that makes it more easily adoptable by production environments. But at the same time, you do want a nice compact notation, so there's a balance that has to be struck there. And another thing is, when the rules have changed, when the actual language rules have changed, you want to make sure it's very different. So if you have a new language and you have a thing called a struct, you have the old language and it has a thing called a struct, you don't want them to mean radically different things. You don't want radically different behavior out of it. Call it something else in the new language so that when you look at it, you know it's different. And it's got to be exceedingly interoperable with C++, because we've got millions and millions of lines of C++ code. It's not going to get thrown out. In fact, what's probably going to happen if we get a new notation is it will be integrated in key places, at least to start with. And maybe that's the language's intention. Maybe you don't try to build a language or a notation that is supposed to address the whole program. Maybe you only use it for key locations. Some reasons why maybe you don't want to do that, but in any case, it has to be highly interoperable. And that means calling in and out of C++, passing data in and out of C++. There are some data parallel systems out there right now that, you know, to get data into it, you basically have to copy the data. And we just don't have time. I mean, the machine is bandwidth limited, so wasting bandwidth copying data into a new container is not going to work. I would say that I'd like to be able to include my C++ headers directly in, because the last thing I want to do is have to keep two descriptions of data formats in sync. So duplicating things like that is bad in a production environment, because you just know that somebody is going to change the C++ definition but not change the corresponding definition in a new place. So very tight interoperability, ideally to the point where you could actually, you know, call inline C++ functions from a new notation and it would figure out how to work them into the scheme. I'm going to come back to that in a second. And you need to leverage the existing C++ environment, because that is the environment that you have to live in, not the other way around. We're not suddenly going to take C++ and shoehorn it into your environment. And that means interfacing to the existing job managers or the existing thread packages and interfacing to our memory management, because game programmers are very anal about memory management. So, I guess a year and a half, 2 years ago, some time ago, I embarked on this experiment. It was a prototype project to see, well, are these ideas you know, worth exploring? And I found this company called Semantic Designs. They're out of Texas, and they have a software transformation toolkit, which is for parsing and transforming the syntax trees and printing them back out. And they do cool stuff like, you know, translate between different languages and whatnot. But they also have some expertise, and their CEO in particular has some experience on supercomputers, so it seemed like a good fit. And we got together with them and we came up with this what we called EA, Vector C++. And it really is just very much a prototype. And they implemented it using their technology, a translator that takes this slightly higher level notation where you talk about vectors of things, and it translates it into loops that process the vectors with the intrinsics for the Xbox 360. Didn't get anywhere near being a useful production tool, but we did learn a fair bit about this whole realm of language development. First and foremost, this is well beyond what EA can do internally. Games company, not a compiler company. We just don't have the kind of research group or development group internally, and we don't have the resources to throw at it. We don't have any of the expertise. So managed to get a prototype built, but you know, that's it. However, everybody that did get to play with the notation and just experiment with the ideas of expressing some of their algorithms in this kind of a notation were all like, wow, this is really cool. Because they could immediately see how it would translate into the low-level intrinsics, and probably how it would translate on different platforms, right? So, you know what, the compiler can take care of all the DMA on the SPUs on the cell processor. It can worry about cache prefetching and whatnot on the Xenon. It can even worry about interfacing to the job manager, so you just write this piece of code and call it, presto, it happens asynchronously in some magical fashion. It's so potentially compelling that, you know, we could write a nice higher level description of code that's actually simpler than the scalar representation. So it's easier for readers to understand, and the compiler has more flexibility in how to implement it. And in exploring all this stuff, you know, there's a whole lot of research out there. You guys know this better than I do about what compilers can generate and languages and et cetera. There's a huge body of knowledge. It just seems like it hasn't made it to our space. And it's probably because we're overly focused on C++. But I gave you the reasons why we're overly focused on C++. So we need something that straddles the boundary there. So back to the APL. This was one of the sources of inspiration. There's a few others, and that list goes on for quite a while. We sort of poked around and saw a lot of different things. Primarily, it just adds vector types, and I'm not going to go into much detail of it because I don't think it's all that interesting, really. But lots of stuff to operate on vectors, obviously. And we never got to the point, because we didn't have any data flow analysis tools, so we never got to the point of this stuff, but it really became obvious compiler needs to be making data layout choices. I mean, because that's how you optimize for bandwidth, the compiler's got to do it if you want the compiler to be able to optimize your code. So it's just a bunch of things that I think the compiler needs to be able to do. And the last one there is if it's going to interoperate closely with C++, you have to be able to get C++ data in and out. Yeah.
How much are you seeing data layout choices not being something that you can do platform-specific, but are really machine-specific, that you need to do differently if someone's got a gig on their machine versus 2 gig? Or
it's usually not total amount of memory. It's usually how many registers a machine has, or really obscure things like how many outstanding prefetches a given machine has. So on the Cells SPUs, you can have 16 outstanding DMA transactions at once. On the Xenon, where it has 2 threads on 1 core, you can have a total of 8 outstanding prefetches. So that means there's a different number of streams you can tolerate to have, and so you might want to split your data into different groups. Another thing is, you know, padding out vectors and how much padding you have at the end, what kind of alignment you want. All sorts of things factor into that equation.
I was wondering how much you're going to be able to statically compile a program for a target platform, as opposed to need to have something that dynamically adapts when it gets there.
I'll come back to that in about 3 slides. So just one example. For a while, I was actually naive enough to think that I was the first person to think of it, because everybody I told this to or showed this to sort of went, "Oh, hey, that's a neat idea." And I think the problem is not many people have thought about how object-oriented and data parallel might get along. Data parallel, often people think, oh, well, I have this big array of all the x's and I have this big array of all the y's. They don't think in terms of vectors of aggregates. But if you have a vector of aggregates in the language, the idea was it could have a member function, and this is where, you know, inline C++, if you might envision that that's actually defined in C++ instead of the vector language. And then you have this line of vector code. So you declare a vector of these things, and you call the member function of the fundamental, not the fundamental type, but the type that makes up the vector. You call it on the vector. And that tells the compiler that we're going to generate a vectorized version of that member that can operate on a long vector of them. But then just like a couple days ago, I was searching the web, and I stumbled across this thing called PC++, which apparently had been under development in the early 90s for massively parallel supercomputers, and they had exactly this idea. So clearly missed the boat on that one. But interestingly, I called that member function shader program because that is sort of like a shader program. That's essentially what a GPU is doing, right? So you describe what you want to happen to a single vertex, and the GPU splats it across a vector of the vertices. So it was interesting because using the Semantic Designs Toolkit was interesting because they have this pattern matching transformation engine. So they run it across the AST, find patterns that match, and then use that to manipulate the AST. But what that really, there's an opportunity there that gave us. Of course, we won't exploit because we're not going anywhere with it, but it just seemed like, wouldn't it be cool if we could add our own optimizations to the compiler? Because we're in there doing this stuff by hand, and we're learning lots of stuff about particular machines and particular ways to do things, and it would be just insanely cool if the compiler is not smart enough to do that. Well, I'll make it smart enough to do that. I mean, that notion just seems really powerful.
Aren't you afraid that you make the compiler do something wrong if your optimization is
Absolutely. I'm saying it was a cool idea. In practice, I don't know how practical it is. Obviously, you wouldn't want anybody extending the compiler. But if we have a core of experts, that core of experts might... Because right now, to use my knowledge, I have to go and optimize that function. If I could suddenly optimize all of the functions potentially that can use that pattern, potentially that's a really big win. Maybe the more efficient way is to go to the compiler writer and say, hey, look at this, and have them implement it. But yeah.
The jobitization or whatever you call them.
Jobification, yeah.
Is that done through an analysis tool, or is that something that the programmers have to do? Actually set up the graph?
All by hand, yeah. Yeah.
So how do you express the dependency of that graph? Because that's also you can't express in C++. You have your own language for describing that?
No, it's all in code. So you say add tree or you say add dependence. You create the job
so
object.
you basically create a library for describing the graph.
Yeah. Because there's a graph, ideally we could describe it some way, some language that's more direct and expressive of it. But because the graph does exist, it gives us some powerful abilities, so we can capture the state of the graph and draw it offline, right? So because we have it as a high-level mechanism instead of, the problem with threading typically is all the mutexes are at the bottom level. So your synchronization and your multi-threading stuff is all happening at a low level of your code. The job manager tends to pull it to a high level and make it much more explicit. And so from a programming architecture perspective, it sort of really has a lot of potential, and as an architect I really like it because it makes it visible as opposed to somebody threw a mutex into their code and throws a wrench into the works or spawns a thread somewhere hidden away inside the code.
So you have implemented your own job library. You're not using like Windows thread pools or whatever.
That's correct. Yeah. It sits on top of the Windows thread pool on the PC, but yeah. And just while I'm still on the subject of semantic designs, one of the things they're really hot on, and they sort of turned me on to the appeal of it as well, is this notion of domain-specific languages, where you can create a small language that is tailored specifically to problems that you want to deal with. And the one place that this really strikes me is if we could have a domain-specific language that is in the conceptual game space where you talk about players and objects, cars or whatever, and that compiler could translate into a model that's more appropriate to the hardware. The problem is translating, what do you translate into? If you translate into native C++, like I've been saying, it's really hard to optimize that, and us building a translator do it, we've already decided, is well out of the scope of what we can do. And really, my job for the last 8 months has been human optimizing compiler, right? We can't do this efficiently. But if we had a target that we could rely on to generate efficient code, so if we could generate 2 vector C++, for example, now it suddenly becomes a bit more feasible because now we can focus on the conceptual to vector transformation, and I think that's probably doable for us in our specific domains. The nice thing about domain-specific languages is you can focus in on a particular problem, and you can use a toolkit that helps you build languages quickly. And the GPU shader languages are something along this line, actually. So I'm down to the last 2 slides, I think. Existing data parallel tools, there's a bunch of them out there in the market. None of them are portable enough for us to use, but we have been looking at them.
Solaware and RapidMine.
Yeah, I wasn't going to name names, but typically I don't like the notations. Some of them are hacked into the environment in a way I don't like. There's this fear of creating a new language, and so they bolt their stuff into the C++ environment in a way that the only way I can describe it is as a hack, and yet they're still creating a new language. They can now say that, oh well, it's in C++. It's not really in C++. You've just bolted it in and limited yourself, really. They don't integrate well. There's all sorts of stuff to do with memory and scheduling and etc. Quite often there's a lot of time moving data in and out of their structures, etc. So lots of issues why, even if they were on all the platforms we have, we wouldn't use them. RapidMind in particular requires dynamic compilation, and on our target platforms where we know the hardware exactly, we don't want that overhead. And it's a meg of memory, and you know what? We care about 20K of memory, so wasting a meg on a dynamic compiler for a platform where the target hardware is always known is just not something we want to do. Plus it has all sorts of ramifications. On the other hand, doing that on the PC is exactly what you want to do because you have no idea what the hardware is until you get there to the runtime. So when talking to first of all, when thinking about our EA Vector C++ thing, and when talking to the vendors of other tools, one of the biggest issues that comes up is how do you debug these things, and how do you traceability? Like, here's my result. How did I get there from the inputs? Nobody seems to have a good answer for it. We certainly don't. We have no idea what it looks like, but it's really, really important, especially if there might be bugs in the compilers or the tools themselves. There has to be a way to debug this code if you're going to use it in a production environment. Otherwise, forget it. And back to the Intel guys for a second. Part of the reason I had been talking to Anwar at Intel was because they have this thing called CT, and Anwar's the principal engineer on it, and he's got a blog that he talks about it a little bit, and they have a white paper they've published, and it too is bolted into C++. It actually looks like a template library. I keep telling them that I think it would actually be better if they cut the strings and went to a new notation, but this is the path they've chosen to go down for now. And they're aiming at nested data parallelism on the PC platform, but they're really interested by other platforms as well, because I think they realize that this software runs on a whole bunch of platforms, and if you can't box somebody in. I mean, the problem with CUDA and all those kinds of very specific languages and extensions to C++ is we can't write one generic version that compiles to everything. We need to be able to compile to everything. It's really important. And these guys, they're talking like they want to do that. I don't think they have anything definite, but certainly that's one of our key points that we're feeding back. And then the other thing is how it integrates into the runtime environment. I've been rattling his chain about how he allocates memory, how he schedules jobs, all that sort of stuff. And the last slide, not too terribly over time. This is just sums up the situation as I see it. At CGO, it was interesting because there was some hardware guys there was some software guys, some academics, and me, the application developer. And we seem to be stuck in this loop, right? I mean, the hardware companies have to build faster hardware, right? That's how they're going to sell more hardware. But hardware is useless if you don't have software that runs on it. But the only way to make it faster is to change how you program the thing, change the programming model, because they've reached the limits of the circa 60s original programming model, so they're going farther and farther out on a limb. Compiler companies, though, and I'm amazed by to what extent this is true. They really are focused on the benchmarks. I mean, I've talked to a bunch of compiler vendors, and they got blinders on. They're looking at the industry standard benchmarks. And all the industry standard benchmarks are in vanilla C++ for obvious reasons. If they were in something else, something higher level, something that could actually be optimized, hey, things would be a whole lot better, but there's no standard to express that in. And then software developers, well, we have to be portable. In the games business, we have to be really fast. But the two contradictory, so we're constantly fighting this battle about how much effort to spend on any given platform, how many things to optimize, etc. We're in an ugly place, which is why I'm here. And then it seems like academia and research, they're always like, and no offense guys, I know you're all research, but it really seems like they're always, well, that's a production problem, or let's blue sky, let's go off and let's think about what we do in an ideal world. But production is anything but an ideal world, right? Production is looking for shorter term solutions, things that integrate into existing environments, and dealing with day-to-day grungy problems. And there's some nice stuff out there in research, but it's completely inaccessible to us. And there's a few things. I mean, RapidMind is something that has essentially come out of research and is trying to go production, but they have miles to go yet. And then it boils down to, if we had a standard everybody could work towards, a bunch of those problems would start finding solutions. People could start moving towards it. But of course, I want it right now. I don't want to wait. And the complete antithesis of having a standard is having it right now, because standards seem to take forever. And in particular, the C++ standard has so much inertia that adding to it or trying to direct it just seems like a losing battle. And I believe that's it. Thanks.
So we have time for questions now. If people have any questions, just feel free to start asking them.
We hit them all during the talk? Yep.
So what kind of tools do you use to debug performance?
Normally on the Xbox 360 in particular, there's this tool called Pix, and it has a really great feature for this kind of optimization coding called instruction trace, and it essentially dumps an instruction stream of a couple of million instructions long, and then you can go in and see where it was stalling on cache misses and pipeline stalls and that kind of stuff. Other than that, for at higher level program analysis, usually we go in and instrument the program. So, you just time how long it takes to get through each section of the program. The tools are rather rudimentary.
And what about the flip side? How do you debug crashes and such things?
Painfully. Usually, this is my strategy. You guys should like this. I develop on the Xbox 360 where I have a debugger that actually does a decent job. And once I have it optimized there, I can port it across to the PlayStation 3. And hopefully it just works. No, it's a Microsoft debugger.
I see, okay.
Yeah, but it's a bit painful. So the flip side of that is, even though it was easier to debug it on the Xbox 360, once I get it onto the cell, the special processors on the cell, it goes at least twice as fast, sometimes 4 times faster. So 6 of one, half dozen of the other. Yep.
Can you separate the multi-core from the SIMD aspects of the problem you're facing? Is multi-core really bad compared? I mean, SIMD seem to be cripplingly difficult in the design. Is multi-core as bad?
Well, it's interesting because it depends on how you go about multi-core. Some approaches to multi-core, like the first generation of products on the Xbox 360, at least within EA, typically they say, well, how can we chop up the program and run it on different threads? Because it was a symmetric multiprocessing machine, they tried to take sort of a traditional approach to it. And then they just found the threads were stalling each other a lot. So instead, now we sort of mostly have moved to a job-based model where most of those other threads are running jobs. And getting it into a job is usually a pretty relatively straightforward thing to do, but you need to isolate the piece of code. And once you've isolated the piece of code, it's sort of the first stage is the same as for vectorization. Before you go in and really start to take advantage of the intrinsics, they're reorganizing the data so that it's easier to chop up or easier to access from another processor, that sort of thing. It's a bit painful, but it's not terrible. And it's only when you want to quadruple or times 10 the performance by doing the single-threaded optimization, the code gets really ugly. But quite often, the Jobification in the first stage of vectorization takes a fair bit of work because they did it wrong in the first place. Question back there.
At the beginning, most of the beginning of your talk was, people are stuck in C++ or game developers are stuck in C++. But then you're talking about need a new language. Let's say there was a new language.
Yeah.
That, what would be the obstacle to a game developer picking it up for the next game?
Well, if you followed the things that I hope for, it's extremely tight interoperability. Really, that's it. If the notation is familiar and it's very interoperable, I mean, the GPU shader languages were like that, and they slipped right in. So it wasn't a problem. The main obstacles are when, some junior programmer has to track down a bug and it's in some weird Sanskrit-like dialect and he doesn't know Sanskrit, right? I mean, it's like random choice. He just he has no, there's a learning curve, a huge learning curve there, right?
So you aren't considering, you haven't been looking at, I don't know, people talk about using Haskell, which is radically different programming-wise, but
Right.
could potentially parallelize and do data parallel and stuff like
And where I really would not want to go that route because most of the programmers would go, that code? So there's this learning curve adoption barrier as well as an integration barrier, like just in terms of infrastructure and environment. So if you nail those, then I think slipping something in there, especially if we have to make this function go faster, so let's write it in this new notation. Once it's integrated into the pipeline, this kind of thing just starts to take over and spread. I think there was one here first. That's you. You're looking around.
Do you feel like there's any way to go for a functional language like that, perhaps, that would be difficult for the majority of the programmers, but that you'd be able to, kind of do centrally at EA and then farm out some kind of API to that they could use? The same way you're thinking of maybe eventually using this Intel library to do data parallel algorithms. Is it really hand-tweaked each time, basically, for each game?
The core functions, you mean, or which?
Well, the things that you tweak, things that you spend all your time tweaking.
Some of them, yeah. I mean, some of them, what's going to happen, though, is these pieces of code that nobody understands will turn into blocks that nobody is willing to go into and change. And so when the feature requirements diverge too much, then it'll probably get tossed out and rewritten from scratch. Although, I mean, depending on how close it is, somebody might bite the bullet and try to understand what it does. Depends on the piece of code.
I think the issue with the functional languages is that you can't really do incremental adoption. Right? You can't just pick up one construct at a time or optimize one piece of code snippet at a time without bending your brain pretty massive.
Yeah.
So you mentioned that C++ has a lot of inertia. You also mentioned the GP programming languages that are already being adopted. So we have HLSL, it doesn't have that much inertia. If you had, you have experience with it. For example, if HLSL could target optimized C++, would that give you enough language flexibility to do some of the things you're looking for? Or
programming model's a bit limited.
Okay.
Yeah, it's extremely vertex or pixel slice oriented, and a lot of this stuff we can't implement efficiently, or even close to efficiently, with that kind of a programming model.
So you need something that's in between the forced data parallelism of HLSL and the complete chaos of C++.
Pretty much.
So you want to still have data parallel capabilities, but not totally restricted to one data unit.
I mean, ideally, this higher level notation could compile that to shaders, a set of shaders with a bit of CPU code that drives it. I mean, if the GPU guys would probably sort of love that kind of environment, right? Because now you don't have to worry about how to shoehorn it into your shaders. Probably won't work on the older GPUs because they have all sorts of weird rules about them, but the newer ones are sort of a lot more orthogonal or closer to CPU design.
at that point is going to be the latency to get it to and from the chip, well, at least on,
That's
especially on PC.
gazillion of issues. Yeah, I'm not saying I have a solution all ready to roll out, but yeah.
If I'm responsible for a math library, and I'd like to know how to optimize it so if the application is running alone, I can grab extra multi-cores, but if it's already several copies running, I stick to what I had called with.
So?
I need to know if it's free space, let me parallelize. Drive all roads, all lanes on the highway at once instead of sticking to one lane.
Right. I mean, we hard code that kind of decision typically and change the policy later when we identify the problem in the profiling. We don't have math libraries operating at a higher level where, I mean, our math libraries are really low level and oriented towards 3D operations, so 4x4 matrix, vector 4, that kind of thing. We don't have fast Fourier transform libraries or large matrix kind of libraries, so we haven't had to deal with that problem yet. But typically when we have to do, when we do have a piece of code, we usually sort of just take a cut at it and see how much sense does it make to chop it into 2 pieces, 3 pieces, does it make sense to keep it on the main core or split it off? And when we go to make the change, it's all done by hand in our particular application context. So, you know, I assume that your math library is probably larger primitives than just, yeah. So I don't have a good answer for you on that one. There's a question over here that's been waiting.
So, In the design, at what level do you think the programmer, the designer of a game has to start thinking about performance, vectorization, parallelization, in order to get code at the bottom that can, compiler can optimize well or can make use of the hardware?
Yeah, that's right now we try to give them guidelines. They don't understand them. One use for the vector language kind of thing is if they start to recognize that the vector language, working in the vector language is very efficient. So they code their stuff and it comes out blazing fast. Those primitives that will percolate upwards and they will start to impact the design layer. And that's, a language like this that I'm postulating here could start out just to implement your kernels. But one impact it really could have is exposing vectors at a higher level. And once you're talking about vectors at a higher level, that helps.
Do that as a programmer just have to think in that manner of doing that.
If
I design a program for performance, regardless of the language I write it in, at the bottom, the compiler can probably do a good job with the code. If I, write a program without that in mind, at the bottom I get some code that, is pretty hopeless.
Yeah, and I've just found that it's really hard, if not nigh impossible, to be able to just talk to people about these things. They need to be able, it needs to be concrete, right? So they have to be able to sit down and do it themselves and say, wow.
And I agree with the language. Has to encourage that, the right thinking.
Right, exactly. And so if the right paradigms can be exposed at a higher level, then hopefully that would persuade them to start thinking that way. Alternatively, there's also this notion on the domain-specific language slide where, well, don't worry about that because we know how to translate from what you describe into the efficient model. So you can play in your nice conceptual toolbox and we can still get efficiency out of that. That's really pie in the sky, but if we don't say pie in the sky things every so often, then it doesn't.
So we have time for one more question, and then afterwards we can have some informal discussion up at the front of the room for further questions.
Any takers? Okay.
Okay, great. Thanks.